तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Yes, the question was if you give me a probability distribution P of x, this is the probability density function, and then from here you have the cumulative distribution function CDF P of x. His question was, suppose you take this random variable and convolute it with itself many times, or the distribution you convolute it many times, and ask as the limit n goes to infinity, will this tend to the Gaussian or not? The answer is no, it will not in general do that, but this idea of convoluting the distribution with itself in a certain sense makes it has a meaning, which is the following. Consider a time series or a set of independent random variables whatever. So there is x1, x2, xn. These are random variables, so I make a measurement for example successively and I get these values for instance. Then I could ask, what is the probability that the largest of these is less than or equal to some number x? That I could certainly ask. So I could ask, let m sub n be the maximum of x1, x2, xn, the largest of these. So I take a huge time series and just take n of these guys at a time and ask, look at the largest one among them. Then I could ask, what is the probability that m sub n is less than or equal to some x, some particular value x in the range of variation of these variables. Of course this immediately implies that it is the probability that x1 is less than or equal to x, x2 is less than or equal to x, etc. So it is automatically equal to probability that x1 less than or equal to x, xn less than or equal to x. But if these are independent identically distributed random variables, this is nothing but P of x raised to the power n. Each of them is independently distributed and it is just this thing raised to the power n, and as you can see, as n becomes larger and larger, it is clear that this probability will shift such that it will shift to the right, the probability mass will shift to the upper extreme, because sooner or later something is going to go larger and larger in its range and eventually the whole thing will be concentrated at the upper limit. But you can ask the following question, suppose I take this quantity mn and renormalize it, rescale it by perhaps subtracting some coefficient, some constant b sub n which depends on n, and rescale the whole thing with, change the scale like we did for the central limit theorem, we divide it by n root sigma. So this is a linear rescaling, there is a shift and there is an overall scale change, and then ask, what about the limit as n tends to infinity of this rescaled variable, whatever this rescaled variable is, and ask, does that go to a limiting distribution? Is this got a limit, does it have a definite limit as n goes to infinity, a rescaled variable, and these distributions are called max stable distributions, and there are only 3 of them. In classical statistics there are only 3 of them, and there are distributions which if the variable runs from minus infinity to infinity, then the limit of this kind of the limit as n goes to infinity of these distributions, the max stable, let us write it down, max stable distributions. There are only 3 functional forms possible for these max stable distributions. One of them is of the form e to the minus x, and let me call these max stable distributions f of x equal to something like this, e to the minus x, and the other one, there are 2 more. One of them corresponds to, the first one corresponds to the variable running minus infinity to infinity, the other one corresponds to the variable having an upper limit. So this is the range and then there is an upper limit, and the third one corresponds to the variable having a lower limit, some finite lower limit up to plus infinity. This is minus infinity to a finite limit, and there are 2 other forms, and they are called the Gumbel, Waals and Frechet distributions respectively. These are the 3 forms. They can all be combined. Well, the other one goes like e to the minus 1 over mod x to some power alpha, and then e to the minus x to the power alpha, where x is positive and x is negative here. So this corresponds to this limit here, and this guy corresponds to this, and these distributions are associated with the names of Gumbel, Waals and Frechet distributions, and they are the only 3 possible distributions, and there are conditions under which arbitrary probability distributions script p of x would tend to one of these 3 limits. If at all they tended to a limit, they would tend to one of these 3 limits, and these are called the extreme value distributions. So these are the distributions of extreme values. If you look at rare events, very rare events, you have lots of spikes in a random variable, and you say I am going to look at all events above a certain threshold, a few standard deviations away from the average, then those extremes are distributed according to these, one of these 3 limit distributions, and they are very, very important in the study of rare events, earthquakes beyond a certain magnitude, avalanches and so on and so forth. So in the study of rare or critical events or extreme value statistics, is a very well known part of statistics, and only these 3 are allowed. Now you could ask what goes to what, and it turns out the Gaussian goes to this. So the extreme events in a Gaussian distributed random variable would eventually, after rescaling, go to this Gumbel distribution, the first one there, and so on. So there is a well developed theory of max stable distributions of this kind. Now you can ask what happens if it is a real time series and they are correlated with each other, these events, then you have to be very careful, but it turns out even if there are correlations among these guys, this still is valid, classical statistics is still valid, except when the correlations become very, very strong. But the point is, if x1, take the kth member here xk and take after xj, and this 1, 2, 3 represent time for instance, then you have to ask what is the correlation between the kth and jth event, and if this dies down like 1 over log modulus k minus j or faster, then this theorem is still valid. So even if they are quite strongly correlated, as long as the correlation is not going to be infinite in extent, in the sense that it is slower than 1 over log mod I minus j k minus j, you still have falling into these things here. The whole thing changes if you have deterministic dynamics. If you have a chaotic time series, then it completely changes, then extreme value distributions can become quite different. I have myself worked on this problem of with collaborators on extreme value statistics in chaotic dynamics, which is very different from what you have here. So this universality is completely lost, but otherwise in most cases, normal cases, this is really true. So that is yet another way of deciding whether deterministic dynamics is occurring or whether noisy dynamics is occurring. There are lots of such tests to decide between true chaoticity and stochasticity or noise of a different kind, and in practical cases it is very important. So I will not go further into this, but that is a good point. Okay. Any other questions? Not anything else? Now I will give a set of problem sheets, couple of problem sheets after today's on probability distributions and other aspects, but we need to move on to another aspect of statistical mechanics, which is perhaps the most important one as far as its power is concerned. You see, I have throughout been saying that thermodynamics is a kind of limiting case of statistical mechanics where fluctuations are neglected and so on, and that fluctuations can be taken into account if you do statistical mechanics, and it provides the corrections to thermodynamics in very many cases, goes beyond thermodynamics, calculates quantities like specific heats which are input parameters in thermodynamics. But now you could ask, is there a place where thermodynamics actually fails, completely no longer valid? The answer is yes. This was the hard problem of phase transitions in matter, and this took a long time to resolve, and it was suspected from the early days of statistical mechanics in the beginning of the 20th century that in principle statistical mechanics, equilibrium statistical mechanics, should tell you everything about systems in thermal equilibrium, including what happens at phase transitions. And a great deal of progress has been made, but this technique does not work all the time in non-equilibrium situations, but in the case of equilibrium problems it works. It is very interesting, it is very deep, and it has connections to quantum field theory, which is where the name renormalization group is borrowed from. What we will do now, what I will do is to pose the problem, is to tell you what a critical point is, show you why thermodynamics fails at this point, and we will not go too much into critical phenomena itself, except a little bit of the phenomenology of the subject is essential to understand. And this will also take us into the subject of real gases, which is what we are going to use as a model. We are going to use the van der Waals gas as a model to describe a fluid. So let me set the stage by taking a very simplistic attitude and asking, what does the phase diagram of a simple single component substance look like, a typical phase diagram. So we will go into the concept of a phase diagram, and we consider an ordinary substance. Water is not a very ordinary substance. I am going to assume that this substance can exist in the liquid, gas and solid phases, and plot a phase diagram. Now the assumption is that the thermodynamic variables that I need to describe the system are 2 in number, 2 independent variables, could be the pressure and volume, could be the pressure and temperature, or the volume and temperature, it does not matter, and these 3 are connected by an equation of state of the system. Of course the equation of state in the gas phase would be different from the equation of state in the liquid phase or in the solid phase, but we are going to cut through all complications and plot first what happens in the pressure versus volume diagram. Every point in this quadrant, pressure and volume are non-negative quantities, so every point in this quadrant is assumed to be a thermodynamically stable state, equilibrium state of the system. But the question is, in what phase is it in, and typically this is what happens, as all of you are familiar from high school chemistry. You have a line that separates the solid phase from the liquid phase. So let me just call it solid here and liquid here, and this line is not to scale, this diagram is not to scale, and basically it says that on this side at this pressure and volume you have, for a given temperature, because the temperature is now found from the equation of state, you have a solid and you have a liquid. By solid I mean a crystalline solid, not a glass or an amorphous solid or something, but typically something that condenses into some crystalline phase. But this thing does not go down forever. What happens is, at a certain stage it typically joins another line, and this line separates the liquid phase from the so called gas or vapor phase, and this line also goes along, and the remarkable thing, the notable thing is that the slope here is much smaller than the slope here, and we will see the reason why. Okay. But these 2 points do not stay as they are. Very typically, generically, there is a third line here which separates the solid phase from the gas phase. Now you are used to this, and we will see what happens as you go down lower and lower in this curve. At some stage it will become a solid, so the thing will cut the physical boundary of this the 2 axes at some point, but for the moment just look at it. Let us just look at this and refresh our memories as to what we learnt in school. This curve is called the liquid gas coexistence curve, because on that, at every point on that curve, the liquid and gas, or the liquid and the saturated vapor above the liquid, coexist with each other. Yeah. Well, we are going to assume that matter exists in only in these three phases. There are many other exotic phases that it could exist in, depending on what you are talking about, and there are many kinds of solid phase, because the first question that should arise is what kind of crystal. We know there are many crystal systems. So in fact there are further complications here. There are phase transitions typically from the hexagonal close packed phase to the body centered cubic and so on and so forth. But
how do you define phase formally?
How do I define a phase? A homogeneous thermodynamic equilibrium system. Now I have to define what is a liquid, what is a gas and so on. I shall do so, but I am just talking about empirical phenomenology. We know this thing here. Okay. A gas is something which you can put in a container, it adopts the shape of the container. Liquid has a meniscus and it remains flat and you can stick your hand in it and stir it around. A solid has got rigidity. The difference between a solid and a liquid is a very tenuous one, we are going to talk about it. It has got rigidity. This is the way I would define it. So by liquid I mean something which does not support shear stress, so it starts flowing if there is a shear, but a solid resists that. That is the way I will naively define this, and we make it precise. Also I know that in general the gas has a much lower density than the liquid, and the particles, the molecules are completely at random, whereas in a liquid, if you look at it very carefully, there is always short range order. It is trying to become a solid, it is trying to crystallize, but the temperature is too high. So this order forms and dissolves and forms and dissolves, etc. But certainly around the neighborhood of any given molecule there is a little short range order, what is called short range order, but if you go 3 or 4 atomic distances away, or 10 of them, it disappears completely. On the other hand, in a solid there is long range order if it is crystalline. So we will talk about this from the point of view of symmetry and order also. This curve also has another name, it is called the boiling curve, because it tells you as a function, I am sorry I should not, you should have stopped me right away, everybody was sleeping. This is not what isotherms look like at all, okay. Pressure versus temperature phase. So this curve tells me, we are going to come to the PV diagram separately, this curve tells me at a given pressure what is the boiling point, and we know that as you increase the pressure the boiling point increases, or as you reduce the pressure the boiling point decreases, so the slope is positive here. The same is true here in general, as you increase the pressure the freezing point increases. Is there an exception? Water is an exception, right? As you increase the pressure the freezing point decreases. So what would happen to that line in the case of water? Yeah, the slope would go the other way, it would still be quite steep, but it would go the other way. So right away it is anomalous, but this is certainly true in the case of generic substances, most substances except a few remarkable substances like water, this is certainly true in general. Okay. So this is also called the boiling curve. This thing here is the solid liquid coexistence curve. It is also called the melting curve or freezing curve, whatever, melting curve is more commonly used. What is this, which is equal to, which is the solid gas coexistence curve? It is possible of course that things will go from the solid phase to the gas phase directly without going through the liquid phase if the conditions are right, if the temperature is low enough and the pressure is low enough, this is what would happen. What do you call this curve? It is the sublimation curve. You might have read in the newspapers that part of the worry about the ice melting on the globe is not just that it melts, but it also sublimates. Quite a lot of it is simply going off into vapor directly. So just measuring how much the water level is rising by is not enough to tell you how much of the ice is really going. So this is a serious problem, and this is the sublimation curve here. all these slopes are positive. In principle this curve goes on forever, but actually it does not do so in practice, because what happens is as you increase the pressure there would be other phase transitions from say less densely packed crystal to a more densely packed crystal, and ultimately at very high pressures things would become extremely densely packed, like the face centered cubic or close packed structure of some kind like FCC or something like that. But earlier there would be other phases like body centered cubic and so on and so forth. So a lot of structural phase transitions go on in this place here. Occasionally what can happen is that this liquid, the liquid disordered phase, can actually, you could have a situation where you have a super cooled liquid, and it is essentially like a liquid but it becomes super cooled, goes into a glass phase, becomes amorphous. Those are metastable states, so we will not talk about it for the moment, but this is what thermodynamic equilibrium states would look like here. What do you call this point here? It is the triple point where you have coexistence of three phases, and a very simple rule called the Gibbs phase rule, which is not very hard to derive, tells you that if you have a single component substance, just one species of molecule, then in such simple substances at best you could have only three coexisting phases at any point, so you have a triple point. On the other hand, if you have more than one kind of species inside, several chemical species inside, molecular species, then of course you could have quadruple points and so on, and the phase rule tells you what is the largest number of such points you could have, phases you could have in coexistence at one particular point. Okay. This point is not all that remarkable, it turns out. There is a triple point. What is remarkable, so let me say this curve keeps going for reasons which will become clear, but what is remarkable is that this curve does not keep going, this curve stops at some point, it abruptly ends in the middle of nowhere, and above that, beyond that, namely at pressures and temperatures to the right of this point, which is called the critical point, you do not have a distinction between liquid and vapor, liquid and gas anymore. So this point is very, very important, it is called the critical point. Okay. And that is the point at which conventional thermodynamics fails, and we will see why this happens. But above this you could ask what is to the right of this? Well, to the right of it you have a homogeneous fluid phase, but you cannot tell the difference between a liquid and a gas, you cannot tell whether it is a liquid or a gas. Now what is it that distinguishes between a liquid and a gas? What do you need to go from here to here? Suppose I start at this pressure and I cross this line at constant temperature and I go in this path. So here I am at liquid, here I am at gas. What have I done? I have put the beaker on, taken a beaker of liquid and heated it, supplied heat to it, kept the pressure constant and let it go into gas. What do I need to supply to the liquid to do this? I need to supply latent heat, right. So in the process a certain amount of heat is necessary to take you infinitesimally close to this point here to that point across this phase transition line. This line here separates two phases, it is discontinuous, the transition is discontinuous in a certain sense, because the density of this system changes discontinuously, it jumps from the liquid phase to the gas phase, and I need a latent heat. As I go up this curve, the amount of latent heat needed to do this becomes less and less till the latent heat vanishes at that point, and beyond that there is no distinction. What else distinguishes a liquid from a gas? Well, there is certainly a surface, so there is surface tension, so that too vanishes at the point, critical point. So the surface tension decreases as you increase along this curve, as you move up, till at the critical point the surface tension vanishes. So the meniscus disappears and then you have a mush. So the phase above that is relatively simple, it is just a homogeneous fluid phase, but below that there is a distinction from here to here. Yeah.
How does it happen that both of them go away at the same point?
Well, that is the way nature is, right, many other things happen at that point. So this critical point, all distinction between a liquid and a gas disappear. that is what is observed. This is what.
Are they correlated?
Yes, of course, yes, all these properties are correlated, definitely. Yeah. So everything that distinguishes a gas from a liquid disappears at that point. Even the densities start matching, because you see I could also draw this in the so called T versus V plane and ask what does this curve look like at that point. Well, actually what happens is, it is clear that the volume of the gas is much greater than the volume of a liquid. So if you are at the liquid phase, you are on this side, a little bit on this side, and you go on changing the temperature, the curve by which this volume would change would look like this. On the gas side, however, the volumes are much larger. This is not drawn to scale, so you end up with a curve like that, and this is certainly not to scale because the change in liquid volume is not all that high, not that great, and this corresponds to liquid, that corresponds to gas, and this is the critical point. Let me denote by now, let me start by saying this is T sub C, the critical point. So here on this curve too I write Tc, and this is the critical pressure Pc on this side. The Vc, the volume, critical volume, is known in terms of Pc and Tc because there is an equation of state, and presumably the equation of state for the liquid and the equation for state for the gas would give you identical results at that particular point if you could write down both these equations. So this is Vc. And the question is what is happening inside. So you see in this diagram, if you are on the curve here, you are actually in a whole region here on this place. So you could be anywhere in this line on this region. So this what looks like a line in the PT diagram has become a region in the VT diagram here. That portion is gas, this portion is liquid, and what is the region in between? That is the region of coexistence of the liquid and the gas. Now you should ask the next question, what will a physical system do? What will it really do? Well, the answer is, if you bring the system to that point, as we will see, it will split into a portion will become liquid, a portion will become vapor above it, and there is a definite rule which tells you how much of this and how much of that. But the important thing is the difference between the gas volume and the liquid volume vanishes at this point. Both these branches come together, and after that there is no distinction at all. So this is a homogeneous fluid phase, this is the liquid phase, gas phase, liquid phase, and this is the coexistence region. Okay. Again you see something strange is happening at the critical point, at this point here. This distinction is disappearing, the curve has got a tangent there, and so on and so forth. Okay. Now of course what one should do to understand this more thoroughly is to draw the third diagram and ask what does it look like in the PV plane. You draw isotherms in the PV plane. I will come to that in a second, but let me say the following. Let me say that we are not going to consider this transition, which except to make some noises about it, or this transition, but later after I do phase transitions a little bit, we will look at other substances like some exotic substances like liquid helium or helium for example, which has all kinds of phases. At very low temperatures it becomes a superfluid and so on. We will come to that separately, but the point I want to make here is the difference between the liquid and the gas here is manifested in the difference in the density. I could also plot the density because that is the reciprocal of the volume for a given number of molecules. It would just be inverted this direction. That difference in density goes on vanishing till you hit this critical point, and then the difference disappears. Therefore what one says is this is a discontinuous phase transition because it jumps, this density jumps. On the other hand, at the critical point the discontinuous phase transition becomes a continuous phase transition because this density no longer jumps, but it is still the limiting point of phase transitions, and this is the modern definition of phase difference between phase transitions. Earlier there was a classification given based on what happens to free energies and so on, where people used to call them first order phase transitions, second order phase transitions, higher order phase transitions and so on. I will explain what those things mean. They refer to the fact that a first order phase transition refers to the fact that the first derivative of some free energy is discontinuous, jumps. That would typically be the volume in this case, because if you differentiate the Gibbs free energy with respect to the pressure, you get the volume. On the other hand, if the first derivative is continuous but the second derivative is discontinuous, namely the curvature is discontinuous, you call it a second order phase transition. Now I have already mentioned that second derivatives are typically things like specific heats, compressibilities, susceptibilities and so on. If that changes it discontinuously, you call it a second order, and similarly for third, higher and so on. But the modern definition does something slightly different, does not bother about this, because there are all kinds of mixtures possible. Instead you talk about continuous and discontinuous first transitions. So you have a line of discontinuous transitions or first order transitions ending in a critical point which is a second order or continuous phase transition. A point of continuous whereas this line, the coexistence lines themselves are lines of discontinuous or colloquially first order phase transitions. So typically first order phase transition ends in a critical point which is a second order phase transition point in the old language. Our idea is to understand this curve and ask why does this happen, can we explain why this happens, and can we see what happens at that point, and can we say something more about this here. This is our immediate goal as I explained. So for that let us go over and look at the third diagram, the PV diagram, the isotherm corresponding to this. Okay. And now I am focusing only on the liquid vapor transition, only on this transition. My idea is to just look at this curve and see what happens there. Okay. Now of course if I took an ideal gas PV equal to RT, then the isotherms are just hyperbolas and nothing much happens, and I could say, well, at the highest temperatures you do have something like that. At very high temperatures, high compared to the critical temperature, this is what happens. Now you see immediately the existence of a critical point provides for me a temperature scale. It tells me there is a natural temperature associated with the system called the critical temperature, and when I say very high temperature I mean something much higher than the critical temperature, and it looks roughly like these hyperbolas, Boyle's law or whatever it is. These are the isotherms. Okay. But as I come to lower temperatures I should really look at the some equation of state which is going to give me take some cognizance of the fact that these particles attract each other. There is an attractive interaction, and typically one looks at the van der Waals equation of state which has all the essential features you need. And what did that equation look like? It said P plus A over V squared times V minus B equal to RT for 1 mole of gas. Okay. And this is a cubic equation in V. So if you keep T constant and plot P versus V, you are going to get a cubic curve of some kind because it involves a cube of V, and very typically it looks like this. Again this is not to scale. In reality something which obeys the van der Waals equation of state would not look like this at all at low temperatures. It would be an extremely steep thing, a very sharp rise here and then a very slow fall off there. In fact the slope here can be 3 or 4 orders of magnitude greater than the slope there. Okay. And why is that? Because this equation really describes two phases. It describes both the liquid phase as well as the gas phase, and that slope there is directly related to the compressibility, because we know that on an isotherm the isothermal compressibility K sub T equal to minus 1 over V delta V over delta P. So this slope here is extremely steep because this guy is highly incompressible. On the other hand, if it is very flat, it means that it is very compressible, and then you have a gas phase. So it is natural to ask whether these two portions really describe the liquid and gas phases or not, and it turns out yes, in the simplest models this is true. Now how would a curve like this go into a curve like that? So it is clear that this is an isotherm for T less than Tc, and these are isotherms for T greater than Tc, in fact much greater than Tc. How would this guy go into that? Well, it could happen by the minimum and the maximum coming together and then disappearing. This would typically what would happen. And what do you get when you have a minimum and a maximum come together? So this guy goes down, that guy goes up, and at some stage you have an inflection point. So at that stage you have some curve here, this curve keeps getting distorted till at some stage you have this, and there is an inflection point here at this place. So let us draw a sequence of, and then below that, immediately below that it does this, and then it broadens out, and so on. I am not drawing this too well. Etc. And there is a critical point, a critical isotherm, where you have an inflection point, and then it goes up in this fashion. Okay. So it is natural to ask whether this is Pc, this is Vc, and this is T equal to Tc. This is called the critical isotherm. So the van der Waals equation of state is a good model for the liquid gas phase transition. It is just an empirical model, but it has the possibility that you can actually see where the critical point comes from. Okay. Now the question is, what is the coexistence region? Can I identify these guys in this place? Well, the first problem that arises is the following. The first problem is this equation can't be right completely. Before I do that, how do I find this thing here? That is not hard to find, because at this point you have an inflection point. So you have delta P over delta V at constant T equal to 0 at Tc, Tc, Vc. At the critical point the slope is flat, and the second derivative is also 0. So you also have this. And you have the equation of state. So in fact you can find the critical point if it exists quite uniquely, because you have 1, 2, 3 equations connecting 3 variables, and you can solve for all of them. I leave it as an exercise to you to find out what is Tc, Pc, Vc for that particular equation of state. And as you are aware, if you take these critical values and you divide by them, you get reduced pressure, reduced temperature, reduced volume, which are dimensionless quantities, and you can re-express this equation of state. And one of the big holy grails of the 19th century was to find out whether there is a universal equation, a single equation for all substances, and the answer is no, there is not, because as I explained, the reason why things condense and so on has to do with interactions, and these interactions cannot be modeled very easily. There is no universal way of doing this, and we know typically there is very short range repulsion, and long range there is attraction, and these are model dependent quantities. So while there is no equation of state, universal equation of state, some things do become universal independent of the substance at this point, and we will see what they are. Okay. But this, as I said, this equation can't be fully correct, and the reason is that if I plot, if I connect all the minima together and all the maxima together in this fashion, then in between the minimum and maximum, I have not drawn this too well, this curve goes up in this fashion, and it says if you increase the volume the pressure increases, or if you increase the pressure the volume increases at constant temperature, and that is absurd, because it violates the fact that the compressibility cannot be negative. So it is not stable, this is against thermodynamic stability. So this part of the curve can't be right, this portion has to be wrong, the portion where delta P over delta V is positive, making the compressibility negative, that is not possible, it is unphysical, and it is unphysical because this is after all a model. and it has its imperfections, and one of them, a very serious one, is that this curve cannot be correct between the minimum and the maximum in between. So we delete that, we will say this is unstable, this portion is unstable, something else happens altogether. Well, what can happen? Follow what happens as I decrease the pressure or increase the pressure on an isotherm. So I start here and it is in the gas phase, this is the liquid phase on this side, I increase the pressure on this system, so the volume decreases. Normally it would have started going down again in this fashion, but that is not possible, so it jumps to this point here, and after that as I increase the pressure it has now become a liquid. So what has happened now is that I took a gas, I increased the pressure on it and the volume shrank till at some stage this fellow just became liquid, condensed, and after that it was not so compressible after that, and I had to increase the pressure a hell of a lot more in order to make small changes in the volume. Fine, but if I reverse the procedure and start in the liquid phase and slowly decrease the pressure on it, keeping the temperature constant, it starts slowly expanding till it comes here to this point, because it still continues on the liquid branch, and then jumps to this place because it has nowhere else to go, and then becomes a gas and runs. So in the forward cycle and the reverse cycle, in this expansion and contraction, the phase transition is occurring at different values of pressure. What do you call this phenomenon? It is called hysteresis. There is hysteresis because that is exactly what happens in the case of the magnet. As you know, when you start with a ferromagnet and you cut off, and there is going to be a deep analogy, and you decrease, you have a ferromagnet that has got a remnant magnetization in the positive direction, and you decrease the field to 0, it still has a permanent moment, and then you got to give a negative field before you make it 0, and on the reverse cycle you have to do it at a different point, it changes at a different point, you have to give it a positive field in order to make the magnetization 0. This is hysteresis which happens in magnets, but you now see this is going to happen according to this even in a liquid gas system, but phenomenologically, experimentally we know this never happens, it does not happen. So that too is wrong in this model, and therefore just deleting this region is not enough, no hysteresis happens in this phase transition. If it did, your refrigerators won't work, because that is what happens in your refrigerator, there is a condensation and evaporation cycle and there is no hysteresis. What happens instead is the following. What happens is you come along and at some point in between, so let us draw it on this curve, you come along, instead of going all the way up there, at some point here it decides to condense, becomes liquid in between the minimum and the maximum at some particular point, a very specific point, and then on the way back when you come down at exactly the same point it jumps and does this. So that is what is observed, and at a higher temperature it is again observed, a similar thing is observed, that is it. So what is happening is that the van der Waals gas, the equation of state is not accurate, you must remove not only the unstable region, but you have to remove a slightly bigger region also, and if I plot that more correctly, the envelope of that goes like this. So if I draw just that portion just for clarity, you have a situation like this, and in between we have a situation like this, and this is V, this is P, this is Vc, this is Pc, and at this point this is the critical point where you are at Pc, Vc and Tc on the critical isotherm. This region is unstable, this is the region between the minimum and the maximum in the van der Waals isotherm, but this region is the real region where it changes from a liquid to a gas to a liquid and liquid to a gas at this point, and this curve, this portion is called a metastable region. And in practice what happens is it switches from one to the other abruptly. So now you could ask, what happens if I took the system at this pressure and volume and simply dropped the temperature instantaneously? I quenched it so that it fell into this point, I quench it down, and then I make the pressure and volume this, and ask what is going to happen. Well, what happens now is that instantaneously phase separation occurs. A portion of it becomes liquid, a portion of it becomes the vapor above it. So a quench into this region will immediately cause a phase separation, with a definite amount becoming liquid, a definite amount becoming gas, and then they are in thermal equilibrium with each other. How much is liquid, how much is gas can be computed in this model. It is very easy to compute. There is a general rule for this called the lever rule, which I will talk about, but this is what happens, and therefore you can see that is the reason I called it the coexistence region, because this is where the liquid and gas coexist. So you quench the system in here, portion of it goes there and a portion of it goes here and stays here. Now the reason this is called unstable and that is called metastable is because in other phase transitions the mechanisms are such that the unstable portion would immediately, a very fast mechanism would operate by which it moves to the boundary, and then the metastable region can be slowed down. In the case of liquid gas this is equally fast, it is practically equally fast. This curve is called the spinodal curve, and now you have to go beyond normal linear thermodynamics to understand this, and there is a whole history, there is a whole subject of these spinodal curves and spinodal decomposition and so on, but this is of technical importance, because when you look at binary alloys, you look at alloys in liquid alloys for example, this or even solid phase transitions of this kind, then the metastable portion can be made extremely slow. You can take hours, you can take days, you could take years for it to happen, and that is why it is very important to know what you are doing here, and there are definite mechanisms for how nucleation and growth occurs to cause this phase separation. That is a subject by itself, I am not going to get into it, but right now I just want to say that this portion here has to be put in from outside on the van der Waals isotherms, these coexistence curves. Then what does the system look like? After that the PV diagram with that correction looks like this. So you have these isotherms, and then you have this guy here, and then you have this, etc. This is the critical point. This is the coexistence region, which includes the metastable and the unstable regions, and this is the critical point, and above that you have this homogeneous phase. So again now our phase diagram is complete. This is what it looks like in the PT plane, this is what it looks like in the VT plane, and these horizontal lines here, these are called tie lines. They would correspond to tie lines here in this fashion. Okay. So this is what the phenomenology is. Our idea is now to try to understand where does this come from, what do we do, how do we explain this. I ought to mention that there is a definite way of finding out where this tie line should be, and that goes all the way back to Maxwell. The rigorous derivation of this is a different story altogether, it is not universal, it depends on the system, etc. But there is a crude hand waving argument which Maxwell gave an argument which is not quite correct technically, which tells you where the tie line should be placed. It is not placed at the halfway point between maxima and minima. In fact the curve I have exaggerated, the curve actually looks like this. A more realistic curve looks like this. This is what it looks like, and then the tie line is placed at some point like this in between, such that the area here is equal to the area there, and it is called Maxwell's equal area rule. So that is the rule, not halfway between the maximum and minimum. So where does this transition occur? It occurs such that the area here is equal to the area there. Now we can understand why that is so by the following argument, which is not correct technically, but which looks convincing at first sight, and let me give that argument. Let us invert that figure, flip it round by 90 degrees so that you have P versus V here. Then what would that curve look like? I am not drawing this to scale, but it will look something like this. This is what happens if you flip that curve around and draw it in the PV plane, and then the question is, where is the tie line? So I want to understand where to draw the tie line. Let us give it some names. Let us call this A, this point B, this point C, this point D, this point E. And this is in the V versus P plane. Now let us consider the Gibbs free energy. Remember that at these phase transitions, if you keep the pressure and temperature constant at a particular phase transition, then the Gibbs free energy per particle is the same on both sides. The change in the Gibbs free energy therefore is 0. Okay. So let us use that fact and let us write G is U minus Ts plus PV. Since I do not remember dG, let us work this out. This is du, which is TdS minus PdV plus mu dN, which is a fixed amount, so dN is 0. That is du minus TdS minus SdT plus PdV plus VdP, and of course these guys cancel. That was the whole idea of this, and therefore this is equal to minus SdT plus VdP. This fashion. And now if you are on an isotherm, dG equal to VdP, because dt is 0 on an isotherm. So let us compute what dG is to go from A to E. So integral A to E dG, the integral to go from A to B plus integral B to C plus integral C to D plus integral D to E VdP. And this must be 0, because at A and E you must have exactly the same Gibbs free energy. Either in the liquid phase or in the gas phase you must have the same Gibbs free energy for a given number of particles. But what does A to B, the integral A to B is this area under the curve all the way down, the full area. But when you go from B to C, you cancel off this area, the one below it, and therefore it leaves you with just this portion. That is the sum of the first two terms, A to B and B to C, plus C to D, it is minus this area, and then you add D to E, you add this area, so it is equal to minus this area, and it says this area minus this area equal to 0, which says the two areas are equal. Now this was Maxwell's tie construction. Tie line construction. Not quite rigorous. Why is it not rigorous? What is wrong with this argument? What is wrong with this argument? It contradicts what I said a little earlier. In what way? Pardon me? Pardon me? Yeah, it goes through regions of unstable, thermodynamically unstable regions. That curve cannot be there. I mean, it's not a, these are not thermodynamically stable. This cannot be a thermodynamically stable state, a line completely. So it's not rigorous, but it's empirically found to be true. Okay. Then the question is, why does that happen? And there are theories which will tell you why the tie line construction is so. And let me give an analogy here at the end, since that's the simplest way to understand. You see, what's really happening is that you have a situation where you're going from one stable state to another stable state in between. So some kind of, in some configuration space, some minimum here to another minimum here. So look at the way the following happens. I start with a curve in which there is a minimum. This is just completely general considerations, and then at some stage it develops, if I change some parameter, it develops an inflection point. As I change the parameter further, this inflection point does this. I change it a little further, this guy comes down, and at some stage it becomes equal minima, and then it starts creeping the other direction. And eventually it does this, and finally the minimum goes to the new position. So this is the left well and that is the right well. I start with the left well, with the right well, so let us call this right, and then this becomes the left, this is the right, left, right, this is left, right, this is left and fully left. So what happened is, if I put a ball here and start doing this jiggling around, there will come a stage where it will fall into the right well, the wrong well. So where does it happen? Nothing happens here, 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 but here this becomes unstable and it falls into this guy here. So the transition is happening at this stage. So it falls, till then it was here, it is happening at that stage in the curve. But if I start at this point and reverse it, so I start here, it remains here at this point, it remains here at this point, it still remains here, it still remains here, and at this stage it falls into the right. So the phase transition is happening at this point here. This is hysteresis. That is the mechanism behind hysteresis, that the change in shape of a generic double well potential, it leads in a natural way to hysteresis, and now you can have different possibilities. This is what would happen in the mechanical case, but there are other situations where it would happen in the symmetric case. It could tunnel from here to there or there to here, fluctuations could push it in, etc. So you have many possibilities of these transitions, and it depends on the system, it depends on the mechanism that you need. The Maxwell tie line construction happens to work when something like this is valid, when there is some equilibrium in terms of energies, some free energies, and then the system moves from one to the other, whereas a purely mechanical system would display that kind of hysteresis. So there is a branch of mathematics which is related to, which is called catastrophe theory, where people talk about the changes of shapes of these generic potentials and what would happen when you have different possibilities. Incidentally, since I mentioned that this is thermodynamically unstable, it turns out that you cannot have a free energy configuration like this, it violates convexity relations. So you need to have what is called the convex hull of these potentials. So you need to have what are called surgered manifolds, you have to do surgery on it and so on and so forth. So there is a very extensive theory of these things, but in very simple naive terms, this is basically all that, the reason for hysteresis in various situations. So this argument, while it is not rigorous, it still gives you the right answer, okay? And then the question is, how do you justify it? But that, as I said, is a different question altogether. So this is what happens in a typical system. Now our task next is to see what happens near the phase transition point, and also to understand why such a critical point does not exist when it comes to the liquid solid transition. So we will talk about symmetry and symmetry breaking and so on. So that will start.